Okay. Is there a person or event that influenced your decision to choose the applied mathematics that you chose?
Okay, if you said neural networks, I could have given some examples. Applied mathematics, if there was any person, ironically, it would be John von Neumann, because I saw his theory of games long ago when I was young, and I have been in the shadow of his way of thinking my whole life, really. And von Neumann talked about three great challenges he was into, one of which really was neural nets. People don't give him credit for what he contributed to the neural network field. One was the basis, trying to understand quantum mechanics, what's really going on, and that's a real tough question. He was also interested in economic policy issues and in life. And so I guess I touched 3 out of 4.
Did you ever get to meet him?
I never got to meet him, no.
And you said if we asked about neural nets instead of applied math, there'd be some names?
It would be a little easier.
Uh-huh.
For example, one event I can remember, I had a summer job after I graduated from the Moore School summer course in computers for people. I worked for one summer in Jefferson Hospital, also in Philadelphia under Dr. Karaman, and he had me read a book by Hebb, Organization of Behavior. And I had read things before in artificial intelligence, but Hebb's book really was an inspiration. And one of the first things I wanted to do, I promised my old class back at the Moore School, I would deliver a talk on how do you translate Hebb's idea into a computer algorithm you could use to solve induction problems. And I thought Hebb formulated this idea very well. It should be easy. And then I started looking at it. Oops. I knew enough statistics to know, oops, this can't work. Correlation coefficients can't do all this stuff. You need a totally different approach. And so I had an incomplete in that course, but I kept thinking about it. And finally, sometime around my sophomore year at Harvard, I said to myself, okay, Hebb's idea of building a brain from emergent intelligence of one type of neuron basically will not work, and basically it won't fit how brains do it. However, if you change the problem and say 3 types of neurons, each of which has its own learning rules, so there are 3 learning rules for 3 types of neurons, with that you really can build a universal intelligence. And that's really where backpropagation came from. It didn't come from some effort to do exclusive OR. That wasn't the motive. Backpropagation was just one of the key tools to let you build a full intelligent system. And that's really where the adaptive critic, HDP, came from. And that gives you a universal intelligence, but not as powerful as the brain, and then after that you're levels and levels of greater power of the same basic mathematical principles. Mm-hmm. So that was certainly the challenge I was into. That was pretty clear.
Okay. Good. So some of this overlaps with the question about when you got involved in one of the core technologies, because this was the late 60s, is that right?
Yeah, so when I was an undergraduate, I took the neuroscience course because it would help me with neural networks. But I was already deeply interested in the neural network challenge back when I was in high school.
Wow. And so these are the things that triggered your jump into that technology. And I guess this was your first computational intelligence related activity, was this research that you were doing while you were still a student in the field of neural networks.
Yes, that's right.
Well, what was the major challenge that you faced in your pioneering research? You already alluded to the fact that Harvard didn't think that it was enough to invent the neural network algorithm that is used by 99% of the field, but were there some other challenges in
Okay, well, the first challenge was the one I mentioned of how do you build and understand intelligent systems and map it into the brain. But I learned that hard as that challenge is, a much harder challenge is how to communicate with the human species about that kind of thing. And yes, the experience with Harvard was part of it. I'm told that Einstein once said, or somebody once said, if you come up with a really radical new idea, a new paradigm, you go through 3 stages before it's accepted. And the first one is, it's totally crazy. The next one is, it really doesn't say anything new. And the third one is, no, we did it first. And I have certainly experienced that in spades. And the truth is, I'm still experiencing it today, because backpropagation was just one step on the way. Complete intelligent systems, adaptive critics, are another step. And this backwards time stuff in physics is another step. And figuring out the universe is one thing. Figuring out how to communicate with humans with all of our tribal taboos and hot buttons, even if you can do a mathematical model of it, it doesn't make it a simple system, because there are so many hot buttons and so many tribal taboos and so many political factions playing games with each other. Knowing game theory doesn't protect you from the complicated realities of the world we live in.
Of course, of course. So you have made many contributions throughout your career. Which contribution gives you the greatest personal satisfaction?
In this context, I would point to my 2 papers in neural networks in 2009 and 2012. Even though they don't have a lot, there's a lot of important stuff missing, they tree back to original sources. So they don't tell you how to fill in all the blanks, but they provide the integration of a whole lot of other things that give the details to make it real. So the 2009 and 2012, that's in the computational intelligence field. Mm-hmm. There is stuff in the physics field I'm also kind of excited by, but that's longer term. I do wonder sometimes, will people rediscover it in 50 years? Will I actually get it through the mainstream in the next 5 years? Because it took longer for me to figure out some of that stuff. In fact, I should be totally honest. When I was a couple years into grad school, there came a point when I said, well, I kind of know the basics of how you build intelligent systems. But this quantum stuff is just totally baffling. You know, I had courses from Julian Schwinger, who got the Nobel Prize in quantum field theory, and we got along pretty well. But it was clear there were some really hard problems. And I remember a moment when I thought to myself, should I do my thesis in this area or in the neural network area? And I said, you know, I'm not going to solve this physics stuff even to my crude basic satisfaction. I won't know what's really going on in the universe in time for a PhD. So I'll pick the other one I'm deeply interested in, and then I'll do the other one in my spare time as I figure it out. And I kind of feel this year I've sort of kind of figured it out, but it'll take a long, long time before that percolates through our culture, if ever.
Well, I, for one, am glad that you chose the neural networks path. What do you think that the impact that the Computational Intelligence Society, Neural Network Society, Neural Network Council, and International Neural Network Society has made on you? And of course, you're one of a handful of people who can say he's contributed to all of those organizations.
They have had a lot of impacts, and yet there's a lot of work left to do. John Wynn was at this big neural network conference in Shenyang just a few months ago, and we got really deep into this. In 1 minute, I can't repeat everything. It's really critical that the cross-disciplinary activity has been institutionalized, made credible, been part of IEEE. That certainly saves the next generation from some of the problems I had when I was a lone voice in the wilderness and everybody was saying, this whole field is crazy. And it's funny how many people tried to take credit for it, who later, who in the beginning were saying, this is totally crazy, this is impossible. All of the people who said, no, I invented backpropagation, who at the time said, it could never possibly work. It's pretty crazy, some of the politics of this stuff. But on the other hand, we haven't become as well established as we should be. For example, the control theory community is smaller as a part of IEEE, but they have regular programs, better in Sweden than in the United States. In the United States, they're a little fragmented. But there are programs where you can get a complete PhD in control and learn the different kinds of control and the basic principles, at least in Sweden. But in the neural network field, we don't really have, that I know of, any PhD where you learn what I consider to be all the basic principles for neural nets for optimization and neural nets for prediction over time, drawing on all of the basic mathematical principles that allow you to build, use, and apply these kind of neural nets and connect them to the brain. We haven't yet established this yet, and in our society there are centrifugal forces pushing people away from cross-disciplinary cooperation, making them non-productive, but they have their friends to help them out politically. And to address the real cross-disciplinary challenge, we have a long way to go to get society to pay attention to this challenge.
I completely agree with you. Things get too siloed, and there's a lot of background that it needs to be assembled to really make contributions in this area, and there are a lot of impediments to assembling that background because of the lack of the type of program that you mentioned.
By the way, the tools are also important. Better tools will make it a lot easier. Everybody and his brother can learn how to use forms of reinforcement learning that don't work, and they get taught in classes this is a system that doesn't work. The tools that do work have been used by a few groups to have really great, impressive applications, many of which are proprietary, but we need to get the more powerful tools out to a broader community so that we can get more people playing.
Yeah, that's certainly true. What impact has our society made in engineering and science? I guess that kind of overlaps.
I kind of said that already.
How do you envision the evolution of computational intelligence technologies? Do you see any expected confluence and any potential new entry?
Okay, so here I give a bureaucratic answer, forgive me. It's like a government institution. Every good government institution has a core mission, and then they have to put time into leveraging what they learn from their core mission into other things, and they have to have a balance. At NSF, I think of it as intellectual merit, and then the leveraging is broader impact. But it's not that simple. In the neural network field, we have a very important core mission. At some point in the coming century, if we work at it, we will be able to write mathematical specifications for general purpose learning systems that can learn to predict their environment and to make decisions as well as the smallest mouse can do, to capture that learning capability and connect it to the wiring of the mammal brain. That's a very discrete thing.
Yeah, and very appropriate goal. That would be a huge step forward from where we are now.
And I regard that as a grand challenge to science, at least as important as what Newton did, just as discrete, just as mathematical, just as fundamental, just as game-changing. But we haven't had our way of thinking change enough to accommodate the mathematical tools we already have to pursue this goal. In principle, we should be able to do it in 10 to 20 years, but I look at how slowly we learn new things, how slowly the academic world accommodates itself, how long it takes us to get around to doing things we should have done 20 years ago. And at that rate, I think we'll be lucky if we do it within the century. We could do it faster, but the political barriers to moving that fast are pretty overwhelming. So that's a discrete goal. But that's not the only thing important in computational intelligence. There's news just this week that people in genetics are noticing that this stuff they call junk DNA is a little more interesting. It's possible that on the horizon, maybe 20, 30 years from now, we'll discover there is a possibility for understanding real genetic systems as real learning systems, obviously meta-learning beyond the individual organism, and we may be able to realize what are the adaptive functions that some of this so-called junk DNA is performing. And there's a lot of very interesting mathematics in that area, not totally unrelated to von Neumann's question, what is life anyway, mathematically? So that's another opportunity, but I don't see it really on the horizon yet The mammal brain is clearly on the horizon, and it looks like it's going to take us 100 years. That next one, it might take a little more preparation than what people are ready for right now.
Although the forces are kind of aligning up because of the huge economic incentives for understanding that. Although the economic incentives for learning systems are huge too, if people would only realize how enormous they are. So that sort of relates to the next question about do you predict any scientific or technological breakthrough involving computational intelligence? So I guess the mouse brain, the real understanding of genetic regulatory networks, these things would be huge breakthroughs that certainly will need our technology to do it. Are there some others that?
Okay, but let me emphasize what I was just talking about with genetics is not what people normally call genetic regulatory networks.
Oh, okay.
Normally people are talking about sort of PDE models to characterize what goes on inside the cell, and that's a nice, very primitive way to begin to address some aspects of von Neumann's question, what is life? But there's other work involving things like boundary conditions and eigenvectors and stuff like that, which the Russians have looked into, important to that question. But what I'm really talking about is the larger system of billions of organisms with different DNA living and dying and evolving, and how the structure of the DNA, which is, I guess, part of the regulatory network business, how the structure of the DNA enables a meta-learning capability which is really at the multi-organism level. It's at the population level. And how in the world does this coding system, which I guess does live at the regulatory level, implement a cross-organism learning system? Because it's the learning across the population which really defines that process. It's fascinating, but when I say I think it's too hard, you've got to understand what I consider doable is already considered impossible by most people. So I'm not suggesting somebody go off and do this tomorrow, unless there's somebody brilliant enough out there who feels prepared to try.
Well, it's certainly a daunting problem. The multi-genomics people are scratching the surface, but just barely. It's a huge problem.
Yeah.
Well, do you have any final comments about the whole topic, either the field, the development of the society, the development of the field, what you've life lessons, career lessons that you've learned as you've worked in this area?
I feel a whole lot of gratitude, particularly to Dan Levine and Robert Kozma, for setting things up so that I could talk about those questions at huge length in my papers in neural networks. And in 2 minutes, I won't say a lot more than what those papers already say.
Yeah, so everybody needs to read those papers, clearly. 2009 and 2012, and these are your papers in that field, in that journal. Okay, well, with that, I'll thank you very much for giving us this interview, Paul. And
thank you, Don.
Really a pleasure. Just click that.